Next one, kinetic, the force of kinetic friction. Uh, this time we are looking at horizontal object first. Horizontal object. Okay. Okay. So we just hide the object. Okay. Where are we now? This is pulling an object. Okay, right. So this one too many letters here. So I simplify this on the right hand side, this diagram here. Okay, now this diagram here actually, okay, it actually shows us something like this. One object, it is resting on the surface. Okay, an object is resting on the surface. So when an object, this object here, when it is resting on the, let me use, okay, okay. So this object, this is the object, huh? This is the object. This object, the rectangular object, is resting on the surface. So by resting on the surface, there are two forces acting on it. One is the normal reaction, and another one is the weight of the object. Normal reaction is the support given by the surface. Mg is the weight of the object. So we have two forces acting on the object. Now, besides these two forces, I am going to give it an extra pulling force. I'm going to pull this object. So this object, the F here, is my applied force. They call it applied force. APPLIED. So this is the applied force. I'm going to pull this object along the surface. Okay, so I'm going to hide it. Why I want to hide this? Because this force, I'm going to resolve it into two components. One, the vertical component, another one, the horizontal component, right? The angle here is theta. So the force, the component that is adjacent to this angle is called F cos theta. The component that is away from the angle, there's no angle here. So this component is F sine theta. So I'm going to resolve the red arrow into the two blue arrows. So I split them into two blue arrows. So as a result, we don't look at the red arrow anymore. We look at the blue arrow. Now, when we pull sufficiently hard enough, the object will start to move. When the object starts to move, there will be kinetic friction that is opposing the motion of the object. Okay, so the forces now acting on this object, we can resolve them into the vertical component and the horizontal component. So which one you want to look at first? We're going to look at the vertical component first, okay? Consider the vertical component of the forces that is acting on the object. Now, how many vertical forces acting on this object now? So you look at the diagram. Can you tell me how many vertical forces that is acting on this object? By looking at the arrows, vertical arrows.
I have no idea. Wait. Huh.
Vertical arrow. This is one of the vertical arrows. Any more
Mm-hmm.
vertical arrows?
The net force. This one.
Can you name them? This one is F sine theta. It is one.
Sine theta.
This is the pulling force. Any more other than this one? Sorry, other than this one?
And the N, no?
And any more? Vertical one? F
And
sine
that, no,
theta
that's about
and
it.
one more?
Mg.
Mg. So these are the three vertical component that is acting on the object. And these three components, they balance one another because the object is not moving up and down, so it's not jumping, it is sliding along the floor. So these two, they balance one another. So by looking at the arrow, I say this n and the f sine theta, they are in the same direction. Only the mg is in the opposite direction. So I say n plus f sine theta equals to mg. So the two upward forces is balanced by the one downward force. Okay, so we say that n plus f sine theta equals to mg. So that is the first equation here. N plus f sine theta equals to mg. So these two upward forces is balanced by the downward force. Of course, as I've said earlier, we are interested in the normal reaction. So I make normal reaction the subject of the formula. So I can do this by moving the f sine theta to the right hand side. So the normal reaction is mg minus f sine theta. So now I found out the normal reaction is actually mg minus f sine theta. Any question? Do you know how to
No.
balance the forces vertically? Yes. Okay. Now we look at the horizontal component. We look at the horizontal component. Can you tell me how many horizontal forces are there? How many horizontal forces are there?
Uh, 2.
Ah, correct, two. What are the two horizontal forces?
F cos theta and friction,
Yes,
the
kinetic friction, Fk.
kinetic friction. Sorry. Ah,
Okay, correct. Now, these two forces, if the object is pulled and it is moving, because they say kinetic friction, it is moving. Now, if the object is moving, who do you think is bigger? Who will win? F cos theta win or Fk win? Who is bigger? F cos theta or Fk? Because the object is
F
moving.
cos theta.
Correct. F cos theta is bigger. So here I say the net force is F cos theta minus the Fk. Okay,
Okay.
I copy down here again. The net force, the net force, the extra force, the excess force is F cos theta minus Fk because Fk win because the object is moving in the direction of the F cos theta. So F cos theta minus this one, right? So you use the same principle for our leaf, for the object inside the leaf, right? When you look back later on, you see it's the
So,
same logic. It's the same logic. So F cos theta is bigger, so we take F cos theta minus Fk. And this is the net force, right? The net force is the one that causes it to accelerate. But if you look at this F cos theta minus Fk, we still don't know what is Fk. We still don't know what is Fk. So we come back to this. We come back to this. The kinetic friction, the kinetic friction, as we have learned earlier, is the coefficient of friction multiplied with the normal reaction.
okay.
Okay. So the coefficient of friction, we leave it as mu k, mu k. And the normal reaction we have found out earlier here. We have found out earlier here. The normal reaction is mg minus f sine theta. So I substitute inside here So the frictional force is the coefficient of friction, or more precisely, coefficient of kinetic friction, right? Multiply with the normal reaction, which is mg minus f sine theta, right?
Okay.
So I use this fk, I substitute into this equation here. I substitute into this equation, and what is it now? So the net force is F cos theta minus Fk. Net force is F cos theta minus Fk now is mu k multiplied with mg minus F sine theta, which is the
Okay.
normal reaction. So we are going to apply this to calculate the acceleration, calculate the net force later on, right? So this is the equation
Okay.
that we use. Show the object. Okay, this is the force that we split into two, right? And this is the net force. Because there are two opposing forces, and because the object is moving in the moving towards the right, so we say that the force towards the right will win. It is definitely bigger. So we say the net force is the F cos theta minus the Fk. So
Okay.
that is the net force. Right. Next.